Hey guys, welcome back to my YouTube channel. I hope you guys are doing great. So today we are doing Leetcode Flip challenge and today's problem is design a number container system. So let's see what the problem is. In this problem you have to design a number container system that can do the following. Insert or replace a number at a given index in the system. Return the smallest index of a given number. Okay. You have to implement this class which is given. It has a constructor which will initialize the number container system. There are two functions which you have to fill. Okay, first function is change, that you have to change, like you have to update or add a particular number at a particular index. Okay, and you have to find the smallest index of a given number. Okay, so let's understand first of all what the problem is, okay, and then we'll dive into how we can approach it. Let's start. So this is a test case given to us, right? I have taken this test case. In this test case, if you see, right, first of all, they are asking us to find number 10. Okay, they are asking us to find number 10. Find number 10. Then they are asking us to change index, like change number at index 2 to 10. So like number which will be at index 2 will be 10. Okay, then at index 1 there should be 10, that index 3 there should be 10, index 5 it should be 10. Then they want us to find the smallest index where 10 is. Okay, where 10 is, right? So this is find. So change means that you have to add this number at this particular index, and find means that you have to find the smallest index of this number. Okay, so I hope you understood what the problem is, right? Let's quickly see output of this test case which is given. Okay, so you better understand how, like, what they are asking us in the problem. Okay, so see, first of all, initially whatever data structure you will take, right, we yet do not know what data structure we will use for this problem, but let's say we have a data structure which will tell us what they are asking, right? So initially they are asking to find 10, like the smallest index where 10 is, but 10 as of now this data structure is empty, right? So we will return -1. Okay, so like index where 10 is -1 because it's not existing right now. Then what we have to do is we have to find, then we have to at index 2 we have to add 10. So in this data structure I will add index 2 I will add 10. Okay, then I have to add at index 1 I have to add 10, then I at index 3 I have to add 10, index 5 I have to add 10. Then I have to find smallest index where 10 is. Smallest index is 1, so 1 will be the output. Okay, then smallest index where so where we have to update now, so we have to now update that at index 1 update to 20, so 10 will be removed and 20 will be added at index 1. Then we have to find the smallest index where 10 is. Now smallest index where 10 is 2, right? So 2 will be the output. So this is what they are asking us to tell in the problem. So now if you will see this output, right, now if you will see this output, you will understand that what this output is. Okay, so I hope you guys understood the problem, right? Now we will see how we can approach it. Main question, guys, here in this problem is that what data structure will I use to store the numbers, indexes and all that, right? Initially, like when I was thinking about approaching this problem, right, I thought of using a list, that I will use a list. I will be storing whatever at whatever index they are asking, right? I will store that index. Like if they are asking at index 2, I will store 10. Simple, right? Like list index 2, I will store 10. What's the problem? Now problem, guys, problem with this using a list is that I do not know what is the size of the list. I do not know that, right? There is nowhere given in the problem that the size of the list can be maximum 10, 100 or something. You will be giving yeah, right? So that is why we cannot use a list. Okay, now what other thing we can use? Think about it. If I have to store, right, if I have to store that, like let's say at this index this number is present, so what I will do, what can I do, what data structure can I use, right? So I thought of using a hash map. Okay, simple. So what I will do is I will take a hash map. Okay, this is my hash map. In that, first of all, I have to find 10, right? I have to find 10. So I do not know, I don't see any key here where 10 is, right? So there is no key where 10 is. So I will return minus 1. Okay. Now I will go here. It's saying me that at index 2 add 10. So my key will be 2 and my value will be 10. So this will be my key. This will be my value. So basically, right, this is my value. So basically, this map is storing index to number. Like key is the index, value is the number. So 2 is the index, 10 is the value at that index. Then I go to this one. 1 is the index, store 10 at it. Okay. Then we go to 3 and we store 10 at it. Then we go to 5, we store 10 at it. Right. Now see guys, now is the interesting thing. We are here. We have to find the smallest index where 10 is. Right. Now one way is to iterate and find out where 10 is and make a list of all the indexes now where 10 is occurring. Like these all are the indexes where 10 is occurring, right? Then you have to find the minimum index among these, right? But this is not an efficient approach, right? Because you guys, you have to scan this entire map, right? What else we can do? What else we can do? What else we can do? We can take another map. Now this will be storing number to index. What does that mean? See, let me iterate again. We will iterate again. So now let's start from the beginning so that you better understand. Okay. Let's start. So we are here. Okay, we are here. So first of all, we have to find 10, but 10 is not present in this map. It's not present. So we will return minus 1. Then we come here. At index 2, we will add 10. And here it is number to index. So at index 10, we will have a list. Now you can take a list here, or in Java, you can take a tree set, right? Because tree set automatically sorts your value. And we need to find the smallest index, right? So it will automatically be at the first index. So you can use a tree set. Okay. Or in other languages like in C++ you can use a vector, or in Python you can use a list. But in Java I'll be using tree set. So this is a tree set here. Oh, sorry. This is a tree set here. Okay, and here I will be storing 2. That at index 2, 10 occurred. Then we go to this. So store 1, 10 here, and now 10 is occurring at index 1 also. So now this tree set will automatically sort this. So it will be 1, so it will be 1, 2. Okay. Then we go to this. So at 3 index we store 10, and 10 is also present at 3. So we are updating both the maps. Now we go to 5, 10. So we add 5 here, and we also add 5 here because it's getting stored here. Now see, we have to find smallest index where 10 is occurring. So we will go to this map. We will find out what all indexes 10 is occurring. So 10 is occurring at index 1, 2, 3, 5. And since I have used a tree set, so smallest index will be automatically at the first place. So I will return 1. So if you see here, we are getting 1. Okay, we are getting 1. Now we go back. Now let's see the next case. Now we have to see, very important guys, very important. Now we have to replace 1, index 1 with 20. So index 1 already has 10. Now we have to add 20 here. So this will get replaced. Now see guys, when you are replacing here, right? When you are replacing here, you have to also replace indexes of 10 where 10 is occurring. Since now 10 is not at index 1, right? So 1 should get eliminated from here. Okay, so now 1 will not be present here. Understood? This is an important step when you are updating, right? Updating an index. Now you go to this 10 and you find the smallest index. So now smallest index is 2. So now output will be 2. So if you see here, now you are getting 2. Okay. So I hope you guys understood this first approach, how we are approaching it. Now let me just quickly summarize it. Okay, let me just quickly summarize it. Okay. So see guys, we have taken two maps. We have taken two maps. One is index to number and other is number to index. Here this value will be a tree set because a particular number can occur at different indexes. This tree set is why we are using a tree set, because it automatically sort the values, and we need to find the smallest index, right? So it will be present at the first. That's why we are using a tree set. Okay, whenever we get a value, like whenever we have to add or we add a value, we check whether if it is present in this index to number map. So if let's say 2 is not present, right, we simply add it. Okay, and we add it, and we also add the number to index value here. But let's say if this 2 was already in this map, so we have to update this 10 right now. We have to update this 10 value to remove 2 index from its list, because now this 10 will get updated to 20 or 30 or any other value. And then we will add that 20, 30's combination, like mapping to this index also. So this is like what the approach is, right? I hope you understood this approach. Let's quickly see the code for it. Okay, and then we will hop to other approach, which is same approach only, just for more understanding and thinking process. We'll be discussing that. See guys, first of all, I have taken two maps at the top. If you see, these two maps I have taken. Okay, these two maps, one is the index to number and one is the number to index. Initialized it, both the maps in the constructor. Okay, initialized. Then in the change function, right, first of all we check if the current index is present, if the current index is present in the map. If it is present, right, we get its previous value. And see this one here, if you see, right, this place. Okay, so if what we are doing is that we take the previous number, we check whether we just remove this current index from its number to index map, because now it will get overridden. Okay, then after that we add the current index to the current number to the index, and also update the number to index list. Okay, now when we have to find, right, we check whether the number is present. If it is present, we get the first index of its value, because it's a tree set, right? So it will store the smallest index. Otherwise return -1. Okay, I hope you understood this. Time complexity, let's understand that. So there are two operations, right? One is the change operation and other is the find operation. Okay, so change operation, if you see, we are basically fetching from map, so that is O of 1, like constant, and where we are doing operations on tree set, right, like removing from T set, that will be O log n, because tree set takes log n time to do any operation. Basically it's a red black tree implementation. So red black tree is a balanced self-balancing binary tree, right? So all the operations are O of log n. So time complexity will be O log n. Space complexity is that we are storing maximum O of n numbers. So O of n will be the space complexity. I hope you understood this approach. If you have any doubts, let me know in the comments. Now let's hop on to the other approach, which is kind of similar, only I won't be dry running. I will just give a small dry run of it. Okay, we'll see the code as well. So guys, previous approach, right? In the previous approach, what we did, when we were, first of all, we have taken a tree set, right? We have taken a tree set to store indexes. So tree set automatically sorts the value. Now see guys, when I say that automatically sorts the value, right, you should also think when we are talking something about sorting automatically, right, and first value should come at the first index, you should think of something called as min heap. Because what min heap does, min heap automatically keeps the smallest value at the top, right? So this is what we need here. So we can use a min heap here in place of a tree set. First thing first, that is first thing. Okay, that is first thing, that we can use a min heap in place of tree set or a list or a vector, whatever you're using, whichever language you're coding in. Okay, now second thing is that in change operation, right, our change operation was a bit expensive. Why? Because we were doing a lot there. What? See, in change operation, what you were doing, first of all, you check whether the number is present, and if it is already present and you have to update its value, right, you remove the value from the number to index map, because, right, this thing which you are doing, we can ignore it for now when we are updating a value. We can do this thing, this operation we can do when we are finding a value, like finding 10's smallest index. We can do then. How? Let's see that. Okay, let's see that. So I will be again we will take two maps only. We will take two hash maps. We are going to take two hash maps, and okay, we'll be taking two hash maps. Initially, since there is, this will be index to number, this will be number to index. Now here value will be not a tree set, it will be a min heap. Okay. So initially we have to find 10, but there is nothing in the map, so we will return -1. Then we go to the next. Here we have 2, 10. So at index 2 we have to insert 10. So 2 is not present in the map, this map right now. So we will just simply add it. Done. And here 10 in the min heap. So I will be just visualizing min heap as like this only. So it will be, it will be 2. Then we go here. We see 1, 10. We store it here. We keep it here. Now this min heap will automatically sort, right? So it will be 1, 2. Now we go to this. It will be 3, 10. So here 3 will be there. Now we go to 5. We get 5, 10. Here we will store 5. Okay. Now we have to find smallest index of 10. So smallest index of 10, how we will find it? We go to this map. We find what are the indexes where 10 is stored. So it's 1, 2, 3, 5. Now it might happen, guys, that you will understand. So here what we will do, right, it might happen that this first index is not necessarily where this 10 element is stored, because we have not done any cleanup when we are adding these values, right? Earlier approach we were doing cleanup as well in change operation, but here in this approach we haven't done any cleanup right away. So it might happen that at this index, at any index, 10 is not present. So we will check whether at index 1 10 is present. Yes, it's present. So we will return this 1. We will return this 1 index. So 1 will be the output. Then let's see what will happen. Now we go to this, that index 1 store 20. So you will just simply update it and you will not do anything. Nothing will be done. Nothing you will be doing here in this map. Now see, now you go to this, you have to find 10. Now you will fetch all the values where 10 is present. So it will be 1 comma 2 comma 3 comma 5, this one. Now you will see whether at one index 10 is present. No, it's not present. So you will remove it from this heap. You will remove it. Now you go to the next value, 2. Whether 2 at 2 index 10 is present? Yes, it's present. So the smallest index where 10 is present is 2. So 2 will be the output. Okay. Benefit of this approach is that you are doing cleanup. You are doing cleanup when it's necessary, right? Like when this operation came, then you are doing cleanup from this min heap. In earlier approach, in the tree set approach, you were at this change operation only, right? You were doing cleanup. But in this, when you have to find, you are just matching the value from this map and just checking. So I hope you understood this approach as well, right? I know it's a bit confusing, but I hope you have understood it. If you have any doubts, let me know in the comments. Let me show you the code for this. Okay, so see, we have taken again 2 maps as we discussed. Change operation, we are just simply adding the element. Okay, if it's not present, we are initializing and all that stuff. And when we have to find, right, we are just taking the min heap and we check if the top element, whatever is coming in the min heap, if it is its value in index to number map is what value which we have to find. If it is, then we return that index, else we remove it from the min heap. Okay, we remove it from the min heap. So I hope you understood this. Again, time complexity in this is also O of log n and space is O of n. So I hope this video was helpful. Let me know in the comments if you have any doubts. If you found the video helpful, please like it, subscribe to my channel, and I'll see you in the next video. Bye.